Okay, let's continue. I wanted to make a quick comment about, there were some people coming asking about their ideas for the final research project, and we've been discussing with Paul and Jeffrey about, and also with Peter, the person who was really running the show last year, what is going to happen with your bots, what's going to happen with the machine learning bot, the knowledge-based bots, and all these sort of different versions. And my suggestion for you for the coming week is that you should take this as a motto of the next 10 days. What I really like in teaching is to give people tasks that I don't know the solution of. So I do not know what works, what doesn't. This is what we ask you to do is research, yeah? Which means that things might go wrong, yeah? It might be the chance that you implement something, you come up with an idea, you come up with an hypothesis, you check the hypothesis, you run a week of experiments, and the outcome is nothing significant whatsoever. You perform worse than random with your bot. Don't worry about it. That's what we call research, and that is what about 95% of my time is about, that I have some grand, great, perfect idea, I try it out, I run experiments, and it turns out to be completely wrong and not significant whatsoever. It's about the one research where at the moment you say, oh, suddenly I see something, oh yeah, I've learned something. So there might be the chance that you tune your algorithms, you have a really great model, you have a design matrix with extremely clever features, you run your two machine learning bots against each other and it changes nothing. That can happen. Don't be frustrated, don't think that you make mistakes. It can simply happen that your research assumptions hypotheses are incorrect. And the only thing you have to do is to report on these experiments. And if the conclusion is we've run valid experiments and the result is that my hypothesis, I cannot show that there is significant improvement of my bots given some features and so forth, that's fine. That is what you have to do. So it's not important, it's nice to have, it's not important, it's not crucial to write intelligent agents that outperform any other agent on the world, on the planet. It's just important that you report on your experiments in a scientific, valid way. And why is it sort of, what you have to be aware is that the problem that we ask you to address is one that is really, really something that is state-of-the-art research to be done. So one of the papers that I've given you on the side is this paper. It's an expert-level current plane agent based on a variant of perfect information Monte Carlo sampling. The perfect information Monte Carlo sampling is more or less what is implemented in RDeep. Yeah? It is in the proceedings of the 24th International Joint Conference of Artificial Intelligence, ICHCAI, which is the most prestigious AI conference, apart from some more sort of it's a general AI conference. So there are some specific conferences that are very prestigious. General AI, this is one of the best places you can publish your papers. And this paper is about how to apply algorithms such as the ones you use to the game of Schnapsen. So you can see here, it describes exactly as you do. Our prime example, Schnapsen has a state space of around 10 to the power of 20. This is why this is difficult. So brute force wouldn't work because we would need 10 exabytes to store the state spaces. It's exactly what you've been doing. And based on the solution that he has brought, which I'm sure have cost more than 2 weeks of research that you have, he got a publication in one of the major conferences in our field. So don't despair, but just don't be disappointed. Just do the research and see what comes out. it is a complicated problem. It's a very complex problem. It's a very difficult problem to solve. And we apply state-of-the-art technology here. So things will definitely go wrong. But this is called research. End of preach. So let's get back to our problem at hand. And that was, how can we now that we have a feature space, and now we have decided on the model class, how can we find the best model? And basically the idea was that down here on these two dimensions, we represent our model, depending on the slope, S, and the meeting point with the x-axis, B. So each of those points are lines, and we want to find the best line. And the best line is represented by the point where we have a minimum value for the error function. So, question to you, what would you do to find the optimal model for this training set?
Hill climber.
Hill climber, yes. I'm getting to hill climbing in about 15 minutes. And it's a variant of hill climbing. It's called gradient descent. This is exactly what we're going to do. Basically, the hill climbing means to lift it up one general level, search. You start somewhere here, and you want to get there. So the thing is, you have to sort of find your way through this space to get to the goal, which is the one where the utility value, which is the lowest sum of squared error, is optimal.
You can just calculate where it is.
That's solution number 2. You can calculate where it is. Yes. So here we have the two approaches. We have search, which I'm going to talk about in 50 minutes, and we have the way you can calculate it. Okay, and for calculating, we need the calculus. So here we are. Just to make sure that we are on the same line in terms of the representation, we have a model represented as the value here by Sxi plus b. We have the error of each instance I, defined as simply the distance between the predicted value and the real value that we have from the training. We have the squared error, just the square of this value, and then we have the sum of the squared errors. Error is just the sum over all the possible training exams that I have, and that is what defines my third dimension. Yeah, here we are. And now, as you said rightly, we have two possible ways of approaching this. Either we calculate the point, or we search. Okay, so finding the optimal way by search is going to happen like this. We just are in some point, we check the value, and then we try to find, using a heuristic function, we try to find the way that is closest to this point that leads us towards the way. And then if we move in this direction, we also move in this direction on our choices of the lines. Basically, if you translate this now back, if you move in this direction, you will probably change the b value, so you move your line like this. So every movement in the point space here moves your line like this. Yeah? And the other one is, do it analytically, just calculate it. Where is the lowest point of my error space? And luckily for calculating optima in a function, we have calculus. So who would say this is a sort of piece of cake? Let's move on to something interesting. Okay, fair enough. So I'd probably go slowly. Yeah. So here you can see a function with 4 optima. Yeah. This is 1. Oh no, 3, oh, sorry, 1, 2, and 3. What are the properties of these points? Yeah? They have a 0 gradient, yeah. So basically, this line, if you draw the line, what's called the tangent, if you call the tangent, it has a value 0. So this is very useful for us to have in this, if we have our curve, we have to look for the point which has a tangent of 0. Yeah? Where this line is horizontal. So let's think of the tangent and try to understand what it is, because this is an important notion now in our calculation. And it's a weird notion. It's a really weird notion. And for that, we have this story, this joke that a police officer stops a car, and in this car there is an old woman, so she's driving, and the police officer says, "Oh, you have been driving 70 miles an hour, lady." And she says, "But that's not possible. I've only been driving for 5 minutes." So the point here obviously being that the notion of 70 miles an hour doesn't make sense if you don't drive an hour. It's an approximation of a notion that we all understand what it means, but it's an important distinction that we should make between the property of the point, the moment she's driving, and the officer said, "Yeah, you've been driving 70 miles an hour," and the property of the sort of two-dimensional activity that she has, that over time, if you would extrapolate to an hour, she would have done 70 miles in this hour. And we do something similar with our tangents, and that is basically the tool for this is calculus. And basically what we do is that we calculate the slope of this tangent per point of the function. So now let's look at the idea of the slope. And so to me it always helps to think of in this way when I look at a parabole. I have no idea how to pronounce this in English, so I'll just do something. And the question is, if we want to say what is the tangent at this point, we sort of have to approximate it. And it's basically an approximation from into smaller intervals as possible. So the intervals getting smaller and smaller. So I take a point from this, which gives me a slope of the function between these 2 points. So it's already an approximation. When I would start here, let's say I start at 0, and I take this point, then I have a certain slope of the combination between these 2 points. Now, the closer I get with my point that I choose, the steeper it gets, this connection between these 2 points, until I'm very, very, very close. And I get something that is almost as the slope that I would expect to be here. And if I approximate this now towards infinitely small, then I get exactly the difference between infinitely far points, and this is the definition of the tangent. Because gives me the line that exactly at this specific point gives me exactly the slope of the next point in the function. Yeah, and this is basically a mathematically well-founded notion, and that is the notion of the derivation. So basically, for each point in my function up here, I can calculate analytically the slope, and I can plot the slope of the tangent as a function. And that's the first derivation. Yeah. And then basically, the only thing I have to look for in this function that I've calculated for the points where this slope is 0. So if I have this function as the first derivation of my original function, I just have to look for the points where this function becomes 0. And in learning problems, you usually have only one. You only have minimization problems. So you should then still, in principle, you should still check whether you have a minimum like here or a maximum like here. But in principle, finding the one value with value 0 for the first derivative is already good enough to help to get you a good, at least one of the good models. Yeah. So basically, finding the slope of this function, which I can calculate mathematically with calculus, allows me to find the minimal point in my error space. So now, obviously, the question is, how can we find the derivative? It's something you should have all seen in high school, but as I said, for me, this is about 30 years ago. So I'm really sort of not up to speed here, but I still sort of manage basics. The idea is that you could, if you want to, in a way, see this again as a search problem, like we have seen before, and it's a search by application of rules. So we have this rule set, and this is now written in a probably in a form that you might not be that familiar with, which is a form that is more handy to write when you particularly have more variables, more dimensions, and so forth. So I have another one here, which is a bit more readable for me. And basically, you have this set of 2, 4, 7, 8 rules, and we just have to check whether we can apply them to our formula to derive the derivation. Yeah. So there is, for example, let's take the first example. We have a function 3x plus x squared plus 5, and there is the sum rule. It's a very simple rule where we just say we recursively apply the derivation for the first element of the sum, and to the second one of the sum, and to the third one of the sum. By the way, you two said that you could do this in your sleep, in your dream. So if I talk some nonsense, you have to stop me, yeah? Please. So if you now look at the thing that you get, so let's do this properly. So if we want to calculate the first derivative of 3x plus x squared plus 5, then you could rewrite this using the sum rule into derivation of this plus derivation of this, and so forth. And then you look for the rules that you can apply on these individual elements. And these are the rules, the power rule, which just says you have to rewrite this into 2x. And you have to rewrite the first one into constant multiple rule. You have to get the constant out, and this one goes in. So basically, this is the derivation. Yeah. So it's just applying these rules one by one. And the only tricky bit is, not even tricky, but if you have a function that has a function that consists of a composition of functions, then you have to apply the chain rule to it. So that would be the second example where you want to calculate the derivation of the square. Then you need to apply the derivation to the inner part of the function and multiply it by the outer part where you do the derivation of the outer part. Who says that they would be able to do, for example, the second example? For who of you is that something you know how to do? Okay. And who says, my God, where have I landed here? In which place? Never heard of, never seen. Okay. There is good there are tools for doing this. There is the reader has material on this. It is the basis of these algorithms that we apply. So it might be an exam question for you to do or to understand which of the rules to apply here. Obviously, in the real machine learning problems, the thing is far more complex. So that's why you need calculus next year, probably more than now, because this is sort of very simple algorithms that you can apply the rules to. Yes, so there's a question. It's a good question. I don't know the answer to. I think I wouldn't know how to provide them to you. So because of it's still a bit unclear how the exam will be done. I think it would do no harm to learn them. But I'll answer the question tomorrow, if that's okay. Yeah. So it's just something that you have to look at 3 times. You do it, and you can do it. It really is not difficult. It's a simple application of these different rules, of which the difference rule and the sum rule and are sort of trivial. The product rule is just multiplying the derivation of the one with the original one and add them to the opposite of the two. So if you look at the rules, they are all very intuitive and clear what you have to do, and you just have to practice it a couple of times. So, yeah. So basically what this allows us to do is, if we were in a 2-dimensional space, to find the place where the tangent is a line that is horizontal, so it's parallel to the x-axis. So basically the place where the derivation is 0 is the place where we have our optimal. Yeah? And this optimal then refers to the line that we were looking for to separate our good instances from the best instances. So that helps us find the best model with one problem. And that is that not all of the derivations the derivatives that we can find might be resolved to 0. So you might not find one that is optimal in the sense that the tangent is 0. So this is simply technically not possible to do this for all the functions. The second thing we have to consider is that the way I explained it now was with a line and a function in 2 dimensions. But obviously, we now have an error space that is might be more complicated, and a separator that is not just doesn't have 2 parameters s and b, but might be a hyperplane. So it might have more parameters. So this space doesn't necessarily need to be 2-dimensional, which makes it more difficult to sort of picture the thing in the first place, but also calculate things. So instead of looking at a derivation, which is just a slope of the tangent in one direction, we have to look at the gradient, which is all partial derivatives. So this is the same idea, it's the same intuition behind, but it's a more complex mathematical construction. And this gradient basically gives us a direction in which our error space moves, so to speak. So it tells me that if I'm in this direction and I go one direction in my search, then it gives me a notion of upwards and downwards, or towards the goal or away from the goal in a more dimensional mathematical space. So it's the same idea, but slightly mathematically more complex. Again, something you will see in more detail in next year's machine learning class, but the general idea is the same. The problem is now that, as I said, you can't find the real solution analytically anymore, so we need to find some way of finding the solution anyway, and we do this indeed by search. By search via some kind of hill climbing. And so the analytic solution we've looked into, and now we look at one way which is called the gradient descent, which is the standard way of doing this nowadays, and that is basically picking a random parameter, S and B, and then computing the gradient. So there's also some calculation involved. The gradient gives you the slope at a certain point, and then you move in a small step in the opposite direction. So the slope always goes upwards, and you want to go downwards to the 0 point. So you move in the opposite direction, and you repeat. So basically, you always go to the next point, look, what is the best gradient for me to go? And that sort of guides you through the peaks and of your error space. And the metaphor that Peter uses for this is that You start with a certain point where you have a ball, and you just let the ball loose, and gradient descent looks for the path to go to the lowest point by, at each point, which way is the smaller, or is the steepest step towards the zero value, or the dome value. So now the problem with this approach is that there might be more than one point with a zero gradient, so where the slope leads you to, and not all of them are fully optimal. So this is called the local optimum problem, same as we've seen with the hill climbing before. So it might happen that you sort of start your gradient descent, and you end up in a non-optimal model. Okay, I believe this is the main ideas of regression algorithms using these this method. So what do you have to do following the recipe? You define your problem as a feature space plus a regression problem in this case. For classification, it works more or less the same. You then decide on a model space. So if you can design a design matrix, then you could simplify your model class. And if you have a model class such as a line or a hyperplane, the question is now which one to find. So you plot your possible models with respect to an error rate, and you try to find the minimal error rate in this plot. And you do this either analytically by calculating the derivation or the gradient of this function. And if you can find the points in this function that have the value nil, you're done. You have found the optimal solution. And if you can't do this, which is mostly the case in more complex models, you do some kind of gradient descent or hill climbing approach to find this optimal space, which is an approximation of the real algorithm. So we have in principle, the search algorithms that we looked into in the first week are here also very useful and important. And most of these cases apply some kind of stochastic gradient descent, which is just a sort of an element like we use it now in our game algorithms. The same idea is there. So now the last thing of today is neural networks, which is the tools that have been extremely successful 30 years ago, and really sort of were the big promise of AI 30 years ago, before the research ran into a big problem, namely scalability, which couldn't be solved at the time. So they more or less went into they were forgotten, or they were not very popular anymore until, let's say, 10 years ago. These technical problems were overcome, and nowadays they're the basis of everything that calls itself AI nowadays, more or less. The idea is very simple, and but was very appealing, as I said, 50 years ago, as you saw with the video yesterday, that sort of training these neurons is also the way it's seen that humans develop their intelligence, by training neurons to send signals according to the input that they get, and some thresholds before they sort of send little bits of information with the human neurons, and similarly also with the artificial neural networks. So the idea is that you have some input nodes, and you give some weights to the value that these input nodes transfer to some output node, and this way you can calculate a function with some kind of bias node that is some extra node. And the learning task now is to train the weights of this network so that it can predict a certain function. As I said, showed you before, with the logic example, the Boolean formulas, it was shown that a perceptron, which is this structure where you just have input nodes and output nodes, can learn linearly separable functions. So it couldn't learn this XOR, for example, but it could do already quite some stuff. But as I said, there was some end of to this functionality. It was seen that you needed to add more layers to really get a more powerful learning paradigm. And basically you add between the input layer and the output layer, you add some hidden layers that normally are, the values are not very important for the user. There is a property of these networks that if you combine two linear weighting schemes, that this would simply result in the same expressiveness. So basically, there is some sort of mathematical transformation needed, which is just applying some function, and in most of the cases, it's a sigmoid function. So you take your input function as input and apply some mathematical transformation to it in order to derive your output values. I asked Peter yesterday why the sigmoid function, and he said, "Oh, this is because this works." So it's again my reservation against the machine learning approaches, where sometimes things work without us really understanding why they work. In this case, it basically is that you should apply some mathematical transformation of the functions so that you apparently can look at different dimensions also of the learning problems. And then you can have as input features such as age and height. You have some hidden layers, and you have some output layer which then can be used as classification such as male and female in the example that we've been looking into. And how does it work? We start with the input values. They are combined with some weighting functions, and they produce us a new value, in this case H3, which is the sigmoid transformation of this weighted sum of these two input values. And that is then given through to the output nodes. And if you remember the example that I gave last week or yesterday it was, about the driving car that they had in the 90s, you simply had the input, your 30 by 32 sensor pixel network. You had 4 hidden layers, which somehow translated this into the meaning of the street, what was necessary to see, and it had as output 30 different steering commands. So go left, go slightly left, and so forth. And that was all that was needed, and it was sort of trained which weights in between those nodes were the ones that sort of gave the best combined results for predicting which action was needed, or which action people had used in previous comparable situations. And then in a way, the important point is that you have to you have to train your model in a way that you need to adapt the weights. So remember that each of those errors is associated with some weight, and you have to now adapt them according to the examples that you get. And again, the approach that you take here is the same. You calculate the error rate, where the features now are the weights that you have in your weighting scheme. So the W's are the features, and you can again calculate the error rate in your prediction, and then the task is again to find the minimation of the minimal value of the gradient. The only difference is that in your network learning, you do this step by step. You do a stochastic gradient descent. So you don't calculate the error rate on all the examples, but you take the error rate on a given example, and you walk by small steps in the opposite direction of the gradient. So you're not sort of doing this for the entire test collection, but you go one by one, which might sort of give you a different move. But the technology that's underlying, the mathematics that's underlying is very similar. And then the thing, of course, that's needed, and that's sort of described in this gradient algorithm, if you translate it to this to this neural network problem, is that you have to do some backpropagation. You get an input, you get an output, you get the error rate, and then this error rate is backpropagated to the elements that have contributed to the results. And I will provide in the reader. There are a couple of pages in the book of Russell and Norvig, which I read yesterday, which I think are very well written. I will provide these pages as well. And they give some better mathematical underpinning of what's happening here. The general idea is that you have this backpropagation when you get incorrect results. So you have the analogy is that you have some popularity measure that's given to your decisions that are made, and there is some network of trust between the people in the government. So you have some civil servants, they have some opinion, and and you have the ministers who have some opinion. And then the question is that if you take some decision on the advice of some of your people, so he says that you should take this decision, and he says you shouldn't, and he said this is a bad job, you shouldn't do it, and it turns out that it was a very popular decision, then the trust in this minister increases, and a bit of the trust is also sort of backpropagated down to the civil servants. So basically the gain in performance is distributed and backpropagated to the upper nodes, the lower nodes in the network. So if you get a good news, then your trust into the ones that have suggested you should take this decision increases, and the people who gave you negative advice, your trust decreases. And vice versa, if it turns out that your result was a bad job, then the trust decreases, and then also the people who gave you the negative advice, they also get more. And the mathematical formulation of this backpropagation algorithm is also via the stochastic gradient descent algorithm. So what did I want to say? There was one thing I wanted to say while I was talking about it. So the big problem with neural networks at the time was that there was more expressiveness when you had not just one layer of nodes, but if you added more layers to the network. The problem was that then calculating the weights, learning the weights, became computationally impossible. And nowadays, with the technology now, we can have networks that are layered, which we have far more inner nodes, and that is the basis of the deep learning, so that you can now really build deep neural networks. And we're looking at this a little bit tomorrow. Yeah. There is two more interesting things which I really find exciting about these neural networks now from a more application side of perspective. What you can think of these networks in a way is that you get some intermediate representation of the information that is coded in the input layer, which you translate to the output layer. So if you start doing the experiment that you use a representation for the input layer, you have a set of hidden layers which have fewer nodes. Then basically you reduce the dimensionality of your representation of the information. So you might have a very complex representation of an image. That's your instance I. You feed all this complex information to the network. You let the hidden layer filter out some of these properties and reduce the dimensionality of the thing, and you produce back the same instance. So the idea is basically you train your network on the same instances for input and output, but you try to do it with as few possible hidden nodes as possible in the network. The nice thing about this is that you get a very, very robust representation of the information. So if you have an image that shares important properties of the, if you try apply this network now on new data that you haven't seen before, it will be far more robust at recognizing new images of the same person. So you train on the instances themselves. You make a model that is sort of looks only at the important features in fewer dimensions, and then it becomes far more robust against noise. Another way of doing things is that if you have more nodes, you can produce these images that sort of look like original elements. So this might now take more information out of the original images as possible. So this is called the sort of the autoencoder idea, which I think is really cool. If you train on yourself, you might still learn models that produce something very rich because of the change in dimensionality of your feature space. And there are different ways of using this. So this is a famous one in the last years, but it's rather complex to do, is that if you represent texts as just feature vectors with all the words occurring in it, and you train to recognize a single word using a neural network on those, you can encode in these hidden layers of the networks the important properties of these words, these individual words. And basically then, this intermediate representation becomes a valuable representation of all the information that we have about these single words. And this is an example of what you can do out of this. If you calculate these hidden layers as vector representations of the single words in a text collection, you get similar words in a very interesting way. So the example was, for example, that you have a relation between man and woman, and uncle and aunt and king and queen, and that could then automatically find a relation between a king and queen because of the similarity of the vector representations you got from the neural networks. So these individual words become similar because they are represented in similar ways in these hidden layers of the network. So they contain sometimes very, very rich and interesting information. Where I find this very interesting is that there is now a link between the things that we have in these neural networks that are usually not understandable, there's nothing we can do with them. They are sort of very hidden information. That we might be able to make this more explainable, that we can explain why a neural network assigns some value to some object, some instances. And that is something very important and something we will discuss also tomorrow in the lecture. So thank you very much. I think that was it. Tomorrow we look at depth in networks and the question of ethics in AI.